I'm going to call this junction alpha, beta, and gamma. At which junction do we have the simplest current in, current out? One that only introduces a single line.
Gamma?
Yeah, because I have only two currents flowing in the gamma, one current flowing out. I know one of the ones going in, I know that what's coming out. I can figure out what's going in from the missing one. So what is the current flowing across here? And while people are contemplating what that current is, and we'll mark a few more people here. All right, and the answer is? 1.8. That's amperes. All right. So now I have 4.1248 amperes flowing in and out. Wait a second. I know the current flowing across resistor F. What's the voltage across resistor F? Or how would you find it? What is the voltage across resistor F? Yes, which has been the answer to how would you find it for quite a while now. You get brownie points for just saying Ohm's law at the right time. Okay, so let's actually solve for it. I know the resistance, I know the current, I know that Ohm's law has some sense of existence. So as I'm going across this, would someone be kind enough to actually calculate it?
11.1414 volts.
11.14.
1414 volts.
All right, so now I'm trying to figure out, so we just found voltage, so we can now use, so we used the junction rule last time in order to find the current. So probably we're going to be using the voltage rule or the loop rule in order to find a voltage somewhere. Which path is going to be able to lead us to finding the next current? In other words, the path where we can first find voltage and then find current.
Did we do E?
Yeah. So if we cruise across here, gain 20 volts, come along here, we're going to lose 4.1248 down here, hang a right, or I guess if you're driving left, go across resistor E down here, and then you're going to lose 11.1414, and you should be at 0. So how much potential do you have to lose here in order to end up at 0 here if we go take this path?
8.8586.
I heard 8.8566?
86.
86. And continuing our repetitive pattern here, we have now found the potential loss across that. That does not work. That can't be right.
4.7338.
Yeah, that, did you forget about? Don't forget you're losing 4.12.
Yeah, I forgot that one.
All right, so 4 point what?
7338.
So what do we do now? This side, sit in silence and meditate.
We find the current.
Okay. Sounds like a good plan. So the current flowing across E.
Point 9468
.9468.
amps.
Alright. So we just did a loop rule, so let's do a junction rule now. Which junction? We've already taken care of gamma, so we're down to alpha or beta.
Beta.
I know I have 1.8569 amperes flowing out. I know I have 0.9468 amperes flowing in here, so what else has to flow in order for that to balance? What is the current flowing down here?
.9101 amperes.
9101 amperes. Well, I know the current flowing across D. What's the voltage across D? Or do we need to do a dramatic pause for questions? Okay, then what is the voltage across D?
3.6404
3.6404 volts. We just had 2 resistors left. We last used the junction rule, so now let's do the loop rule. In other words, what is the potential drop across this? So if I gain 20 here, and I lose 4 point something there, and I lose something there, and then I lose 3.6404, and then I'm gonna lose 11.1414, should be back at 0. That's probably the simplest route. We can go more convoluted. I gain 20, I lose 4 point something, I go across that, lose something. I lose 3.6404, I then gain, going this way, 4.7338, I lose 15.8752, back at 0 again. The gain there is that if I go against the current, I'm gonna gain potential. If you think about water flowing downhill, if I'm going opposite the flow of water, I'm going uphill, I'm gaining. Not make this big enough. But what is the potential drop across here?
How do you know which way the current is flowing?
because I have a battery here, and so if I think about the current flowing like this, and we get to here, it has to spread out and come this way. But if, once we had the equivalent resistance, we knew which way, and we figured out what the current is and the potential drop here, just slowly gathering it piece by piece. If it flowed the other way in one of these, then I had 4.1248 amperes flowing this way. If I had 5 amperes flowing down, then that current would have been going that way. So we'd end up with a negative current somewhere. All right, potential drop here,
1.0942 volts.
1.09.
What'd you get?
3.0.
3.4.
Yeah.
3.4?
3.4.
Is there something wrong?
I did it the convoluted way you described, so I was just curious.
Oh, well, the 5 is the which one is it? One of the ones is rounded.
Well, presumably they're all rounded. But
Yeah, but that one had 5 decimal points that we could have gone to.
No, 0.73.
I think it was that one at least. But that's probably why we got different answers if we did it that way.
How close were you?
I think I got the same answer, we got 1.0934,
Okay.
and you got
4.2.
4.2.
They got 3.4. I got 4.2.
Oh. Which is one of the reasons I went 4 decimal places, is we're off by, I mean, there's a difference of 8/10,000ths of a volt. So now I know the voltage across these, one of those, then we can find the current going for one across each of these. 4.2 or 3.4?
The way I did it was going over there. Yeah, I did that one. So
That you did this way?
Yeah.
Let's go with 4.2. Parenthetically. So what is the current flowing across here?
So the voltage is the same for both resistors?
They are in parallel. Objects in parallel have the same voltage.
Right.
In other words, I got a junction on both sides, so no matter which path I take, I have to have the same change in potential. Don't forget, we got an international audience here. We got millions of people who are just waiting for this video to drop.
So what resistance are we using?
That's a 2 ohm resistor and a 3 ohm resistor.
Yeah.
Did I misunderstand the question?
Are we using 2 plus 3 or?
They feel
Because are we
separately.
finding the current right now?
Yeah, we're finding the current right now,
Right.
so if I go this path, I know the potential drop across either of them. So if I go this path, I have that potential drop into that current, or sorry, that resistance. If I go this path, I have that voltage and that resistance.
So we're just doing both?
Yeah.
Okay.
Well, this one's gotta be 0.5471. And this one, negative 0.3647. 7. Did someone confirm or correct?
I got that.
You got that? Okay. Now let's do a quick check here to see how far off we are. I know that if I use the junction rule here, whatever current's flowing across here must join back up. So if I add these two currents together, that should not be negative. If I add these two currents together, I have 5, 4, 7, 1, and 3, 6, 4, 7. I get 8, 1, carry the 1, 1, carry the 1, 9, 1, 1, 8. And we calculated a 4.9101, so we are 17/10,000ths of an ampere off, or 1.7 milliamps. Potentially 5 decimal places would have been better, we would have gotten better results, but it is what it is. I will leave going out to 5 decimal places and exercise for your own input. We still have another half hour to go, but let's not forget test tomorrow on 18 and 19. I think we're ready. 3 batteries, 4 resistors. And a problem similar to the last question on test 1B.
We had one set up, but we never finished it.
Oh, we started it?
Yeah, we had it set up.
Yeah.
Ah, okay. So 12, 10, 8, 3, 4, 5, 6. So let's do that one. The other thing I need to see, up or down? So up, down, down. Volts, 10 volts, 8 volts. And that was 3 ohms, 4 ohms, 5 ohms, 6 ohms. Okay. We can't do really equivalent resistance, or there's one place where we could do equivalent resistance, but it is not really gonna save us from the hard work. So last time, there were 2 methods that I talked about. One was the 1 current per, in essence, 1 current per wire, or there's 1 current per loop. It does not matter which one we do. The 1 current per loop, that is also known as mesh analysis. Anyone with a preference?
What are our options again?
1 current per loop. Wait,
1 current per path or 1 current per loop?
yeah.
Elise, do you have a preference?
I'm just looking at the mesh analysis notes, and it doesn't fill me with joy.
Okay.
So we can do that one.
The one that does not fill you with joy?
Yeah.
All right, I heard mesh analysis.
Yeah.
All right, so I have 3 different loops here. 2 are independent. I've got left loop, right loop, and then the entire loop. I need to identify a current in 2 of them. I typically do left and right, but that's just a me thing. If somebody wants to do the whole thing, we can do that. that a yes?
I'm not gonna sign us up for that, sorry.
I missed that last little moment.
I would be okay with that, but I don't know if they're.
Oh, doing the whole thing? Alright, so we'll do left and home. I also typically make my currents clockwise. It doesn't have to be. Just pick a direction. And I'm gonna call that current 1, which I'm gonna also set equal to B, just so I don't have to keep writing subscripts. And then, seems like, because Laura wanted it, I'm gonna do the whole thing, and that is C. I'm not advocating that this is necessarily the way you have to do it. Of the methods that I've outlined, pick something. Pick one of them, learn it, know it. All right, so now I've identified that. I have 2 unknowns. I need 2 equations. My 2 equations will be based upon voltage. And again, I had 3 different loops there. I need to pick 2 of them. It doesn't have to be the 2 that I've identified here. Matter of fact, when I do my loop, I don't even have to go in that same direction. However, based upon what I'm seeing here, I do suspect that all of our currents will be positive in the end, but not necessarily. Because the direction of my current loop, arbitrary. The direction of my voltage loop, arbitrary. If we have picked the wrong direction, we'll get a negative value for the current. So I'm gonna start here and do, I'll do the left loop. 12. Starting us off. Because I'm going here and I'm going this direction.